Okay. Good morning, everyone. I'm very glad to have everyone here. So my name is Shaohui, and currently I'm doing my PhD in Finland. So today's topic, I will start by introducing my PhD, and then also move on to what I have done during my master in France. So about my PhD, the topic is large-scale estimation of boreal forest leaf area index by airborne LiDAR scanning data. And my supervisors are Laurie Kohonen and Matti Maltamo. So a bit more about myself. I did my first master at about about 4 years ago at the University of Edinburgh in Scotland. And then uh, I continued because I realized I'm very interested in forestry, so I continued my study with another master at the University of Eastern Finland. So the first year I was studying in Finland, and the second year I was relocated to France, where I did this internship with ONF, and also based on what kind of work I further continue with writing my master thesis, which I will be elaborating a little bit more later on after the introduction of my PhD. So, so just to recap on the topic is large-scale estimation of forest leaf area index with airborne LiDAR scanning data. And so why leaf area index is important, I'm sure like many of you have already known the importance of it. So because it's crucial in understanding and monitoring biosphere processes, as canopy is very important in modeling, for example, biosphere and atmosphere variables, and also a leaf area index is very crucial to estimate gross primary production, forest growth, and carbon sequestration in the context of global climate change. And so for now, the traditional method of collecting leaf area indexes turned out to be very expensive and also at the same time labor intensive. And you can always encounter issues about sampling and scaling issues. These are very common in the field of leaf area index. So what we plan to do is to develop some airborne LiDAR ALLS-based estimation methods. So with the help of airborne LiDAR scanning data, we expect to increase the accuracy of leaf area index, and also we try to take clumping effect into consideration to see how to best achieve like a very precise leaf area index estimate. And then the research is going to expand from one study area in Finland, and then we're going to move on to multiple study sites, and eventually, hopefully, we can cover the whole country at the whole country level. And these are my collaboration team. We are mainly people from UEF and Aalto University, University of Helsinki, but also we have some contacts in Tartu Observatory here. And if you are interested in leaf area index, please feel free to send me a message or an email, and I'll be very glad to hear something from you. And then I'll move on to, so this is a very short introduction of my PhD because I only started 3 months ago, and everything is quite new to me as well, but I'm very happy to be on track, you know. And then next, I will move on to, this is the main part of today's topic actually. It's what I did during my master. It's what my thesis is about. So the topic is unit level small area estimation of forest inventory with GEDI Auxiliary Information in France. And I will start by introducing one of the keywords in the title, which is forest inventory. So we all know forest inventory is a systematic way of collecting data of forest resources within a given area. And it plays a very important role in understanding the state and development of forests. And national forest inventory are very well known. They have many benefits that you can find in previous literature, such as they provide information for forest management, and also it's helpful at biodiversity assessment, and also such as carbon monitoring, etc. But there are also issues with forest inventory as well. Well, I'll start with the forest inventory in France. So in France, the national forest inventory has been continued since the year 2005, and it relies on a two-phase sampling method. So in the first phase, it's like so the whole country is covered. It's covered by a systematic grid, and in the first phase, about 1/10 of the grid is photo interpreted with remote sensing data to determine the type of the landscape. And then in the second phase, about 7,000 forest points are manually surveyed every year. So this is how forest inventory works in France. And because of that, to collect information on forest inventory, we have to send out people and experts to go to the field every year. And this is the traditional way of collecting NFI data. On one hand, it's very flexible and mobile because you can go anywhere you want, and it also produces high quality estimates because trees and individual trees in a stand can be like mapped properly. But it also has the downside of being it's costly, and then you have to send out people. So sometimes, especially in a very far away place, it gets like more difficult to access. So national forest inventory, although they provide very valuable information at the on large scale, such as the national and regional level, but it often fails to do so for some small forest areas, such as municipalities. And as a result, developing alternative inventory methods are highly desired, and they should accommodate forest inventory estimation for smaller areas at a lower cost and possibly with some increased accuracy and precision. And in response to that, small area estimation came into being. It is a set of estimation techniques that are able to make predictions for sub-areas of the total population. And it has been reported that small area estimation techniques can help improve forest inventory without increasing the cost. And also it's possible even to make some predictions, even if when some field plots are not available. And the common sources of auxiliary data, which is used to facilitate small area estimation, usually come from satellite-based image, and also with aerial photogrammetry, and most importantly, LiDAR. But in some countries and regions, LiDAR are not always readily available because carrying out a LiDAR campaign can cost some fortune, you know. But the newly launched so GEDI was launched in December 2018, and it's on board the International Space Station. So it's a spaceborne LiDAR instrument which covers most part of the Earth. So GEDI, compared to ISAT, GEDI had a much smaller footprint, which is only like about 25-meter diameter footprint, and it's the first spaceborne LiDAR instrument that is specifically designed to measure and monitor vegetation structure. And this is a little bit more about the GEDI LiDAR instrument. So GEDI has 3 beams. One of the 3 beams is split into like 2 coverage beams. So in total, as GEDI is on the ground, the ground track is moving forward, it shoot out laser fires, and in every second kind of swing a bit, so that in total about 8 tracks are generated on the ground. And GEDI on the right side is a flying pattern of GEDI. So you see that I collect most part of the Earth, but unfortunately it doesn't cover much part of the boreal area because of the orbit issue. And I just checked in Estonia, for example, in Tallinn, it's about 60 degrees. Well, the GEDI only covers about 51.6 north and south. So, but it's in some part of Estonia, it can be also applicable, which makes it quite interesting. And because this study was conducted in France, and GEDI actually basically covered every part of France, even the excuse me, even the overseas territories. That makes GEDI a very interesting application in France. And this is a typical standard GEDI footprint. As you can see, it's about on the left-hand side, it's so GEDI contain information about ground elevation and also some information about the forest canopy, but most importantly the height matrix, and also from the height matrix you can derive the ground elevation and also canopy height and also canopy height models. And this is a promotion video, but I have no idea how to play it here actually. But anyway, I'll send it's a very interesting GEDI promotion video, and I can send the link in the chat later on if you are interested. It's only like 1 minute, but very interesting, I guarantee that. And let's move on to the study area. So it's in the study area was located in the central part of France. It's called Sologne, with about 6,000 square kilometers, with 48% of forest cover, and it's dominated by broadleaf species such as oaks, but also with some conifers like common pine. And the area has 3 smaller areas, which is defined by the French administrative boundaries of department. And this makes the study site a very ideal candidate for smaller area estimation. And then what we have for the data, so we have an FI plot in the past from 2015 to 2019. In this study, we only estimate forest volume, but of course, the same method can be applied to make estimation on other forest variables as well. And for the auxiliary data, we have GEDI level 2B product, which mainly include height metrics and ground elevation. We also have this digital terrain model and forest mask from another French institute, but they're also like freely accessible. And I believe in many countries you also have these 2 products. So the research was to explore the possibility of improving forest inventory precision for a large area, which is the study area of Sologne, and also smaller sub areas like individual department with 4 specific questions. So we want to see whether because there are 2 types of GEDI footprints, so we want to see whether the coverage footprints are equally usable as full power footprints. And we also want to assess how accurate is GEDI elevation compared to, for example, LiDAR elevation. And we want to see what's the impact of footprint distance on its corresponding NFI plot, which is connected by the KNN method. Last but not least, the most important one is to see whether and how can GEDI contribute to small area estimation of forest volume. And then for the first research question, we selected 2 height metrics, with one from the upper range and one from the lower range, RH100 and RH20, and we further look at the statistics of these 2 metrics. We found out that like both types of GEDI footprints are like highly identical, and but there are some deviations existed, for example, in leaf-off seasons, and I've marked them out in the red square. And but if you look at the whole histogram of these 2 types of footprints, you can see they are almost identical. So based on that, we can say that both types of footprints are equally have the same quality, because at the beginning we were not sure whether we should include coverage footprints, as they only have half of the penetration power compared to the full power footprints. But the results show that they're basically the same. So we decided to include coverage footprints because they not only help to increase the sample size, but also it significantly increases the spatial coverage of GEDI in the over the study area, I mean. And then for the second research question, we compared GEDI elevation with LiDAR DTM, and we found out that in our study site, it is both types of elevations are highly correlated to each other. And for us, the bias is about 1.7 meter, which means in the GEDI was like overestimating ground elevation compared to LiDAR DTM. But the R square is very high, and also RMS is acceptable. So, but compared to with other studies from the US and Germany, the bias is a little bit like somehow larger than the studies from US and Germany. And we also found out in a small group of outliers, as you can see on the figure, existed in our data set. And then we further look at these outliers and found out that they are spatially clustered, and they're more likely because of some weather events. And as you can see, it's very, but it's somehow typical, because they also in a study in Spain, I think they also found these kind of a small group of outliers existed. So if you are going to use GEDI data in the future, it's very important to remove these outliers first. And then to answer the third question, we connected an FI plot with GEDI footprint based on the KNN method, and then we used a small area estimation to make predictions of forest volume, and we also based on the distance of GEDI footprint, and we found out at about 200 meter the estimation had the best results. So here you see the RE is means relative efficiency, and it can be seen in a way as using a simple random sampling method, and the sample size would have been to like how many times higher to achieve the same precision. As you can see here that we're at 200-meter, GEDI can improve the relative efficiency by a factor about around what 2.5. So it's actually a very good result, I would say. But this is at the whole study area level, and then we move down to smaller areas within the area of interest, but also under the same distance metric. And then we found out that with GEDI auxiliary data, you can see the small area estimation variance is significantly reduced compared to variance obtained from simple random sampling method. And the model we used here is volume, and the variables are RH120 with forest type. So at each individual department level, the relative efficiency varies, but they're around by like again in relative efficiency by a factor about as high as 2.6 at the whole study area level and as low as 1.6. But anyway, these results are already I would say very much acceptable compared to the simple random sampling method, which is commonly used in the current state of art. And then we had a look. It doesn't work really well. Sorry. I would share my screen here because I think it would be better. Sorry for the yes. Because I put some animations on and it doesn't really work well if I upload it online. So move on. From here, we have the increased relative efficiency. And then to put in a figure, this is the estimation at the whole study area level, and on the right side, it's at each department level. So we see that the variance is significantly reduced with GEDI auxiliary data, but also we found out some smaller issues concerning the one department. As you can see, the estimation is not very accurate, and the variant, although with reduced variance. So, and then we further calibrated the model and look at how much the model can work. And then we found out about 16% of the predicted values are actually outside the calibration domain of the model, which means the model was actually extrapolating if the values are outside the domain, of course. And we found out that a bigger proportion of the points actually come from this department with estimated issues. And then if we look at if we look at the variance at each department, we see that actually Loire actually has the biggest standard deviation in terms of force volume, and also you see the maximum is very much larger compared to the same values from other departments. So because Loire has a more heterogeneous forest volumes. So that's why we think this estimation issue happened, particularly in this department. Which means in future studies, we would encourage you also to calibrate the model and look at to see whether the model is extrapolating or not. So a few messages from today is that both coverage and full power footprints are equally capable of penetrating vegetation and collect forest information, and they can be included at the same time in the future study. And then GEDI elevation actually very consistent and accurate compared to LiDAR DTM. And we would say we found out that a footprint about within the 200 distance away from NFI plots can best represent their corresponding NFI plot information and further used in small area estimation. And then the last one is forest inventory precision can be improved with GEDI auxiliary data using some typical standard small area estimation method. So that's what I have for today. And if you have any questions, please feel free to.
Thank you very much. It was very interesting presentation.
Thank you. So I have the questions here. Oh, so yeah, we included both coverage and full power lasers.